Hello students, welcome to the class of Digital Communication System. We have already discussed the sampling process and also we discussed about the need of digital communication system. We studied the block diagram of the digital communication system. Before we go into the types of sampling, I would just recall what is sampling. Sampling is the process by which you convert a continuous time signal into a discrete time signal. Continuous time, that means the time axis is continuous, means you are taking all the samples in between any two intervals, and the amplitude axis is also continuous, means you are taking all the amplitude. So that is a continuous time signal, and you are converting that continuous time signal into a discrete time signal by using the process of sampling. What we did in the process of sampling, how are we doing it is we are taking only certain instants of time, values at only certain instant of time. And this instant, the speed of taking these instant is decided by the sampling theorem, where we we take the samples at a particular frequency, which is at least double of the maximum frequency present in the signal. So if your signal is having frequency of 50, 100, 200 hertz, the maximum frequency is 200 hertz. So what you are going to do is you will take the samples at a rate of 400 samples per second, and only then you will be able to recover the signal when you are demodulating it. When at the receiver, when you are receiving the signals, you will be able to recover the full signal. Or if you want to convert those discrete time signal again into a continuous time signal, you will be able to recover it only if you have taken the samples at a rate of Nyquist rate or greater than that, means greater than twice FM. If you are taking the samples at a rate greater than 2 FM, only then you are able to recover the signals. Also, one important thing that you have to keep in mind is that the samples that you are taking should cover the full length of the signal. It's not that you can take from in between certain points, or you can take some points in the beginning and the last. Say suppose your signal is from 10 to 100. You cannot take between 50 to 80 and say that I have taken the samples at the Nyquist interval, so I have taken all the samples. You have to take the full length. You have to start from 50 and go till 100, and in between you have to keep a frequency rate of that greater than equal to the Nyquist rate. Today, what we are going to discuss is the types of sampling: ideal sampling, natural sampling, and flat top sampling. As you can see on the screen here I have drawn direct delta functions, or you can say train of impulses. But in these two cases, in the case of natural sampling and flat top sampling, what you have is the rectangular pulses. What is the difference between this rectangular pulse and this direct impulses? Yes, so the direct impulses or the impulse function, the train of impulses, they don't have any width over here. Here you can see a certain amount of width. Now, again, in the sampled signal version of natural sampling and flat top sampling, there is certain difference. See the top of these two signals. So that the top of the flat top sampling is flat, but this one is following the message signal. Same, the shape of the top of these samples are same as the top of the message signal, right? So this is the difference between the flat top sampling and the natural sampling. And you can see the sampling functions that are used. In case of the three are different, like you have the rectangular pulses for natural sampling and flat top sampling, but for ideal sampling, you have the train of impulses. Okay, let's go and into the detail of these things, and the differences will get more clear. So instantaneous sampling, there are all other names also given for this. This is the ideal sampling. It is also called the ideal sampling or the impulse sampling. Here, the sampling function is a periodic train of impulses. You can see over here, this is your periodic train of impulses, delta t. Why is it written over here, t in the bottom? Or you can see in the subscript, with a t is written, this t is what? Your time period of sampling, right? So sampling period, you can say this is your sampling period. So if this sample is at 0 and the sampling period is t, the next sample will be at t. The next after that will be at 2t, 3t this way, and this side it is minus t, minus 2t, minus 3t this way. Switching sampler circuit is used. So this is a circuit that we used for instantaneous sampling. At this point over here, you are giving the message signal. At this point, you are putting a switch. The switch, what it is doing is taking only the values of the signal at certain instants. Say it is taking the value at 0t, 2t, 3t. So this is your method of instantaneous sampling. But here, closing time of the switch approaches 0. So the output consists of only the instantaneous value. Now here, this method is not practically realizable because certain time will elapse when you switch on and switch off the switches. But here it says that the switching time should tend to 0. So the width of the impulse signal should be infinitesimally small or tending to 0. Requires that the closing and opening of switch should not take any finite time or requires infinite bandwidth, which is practically not possible. Hence, this method is only theoretically studied. What does it mean? Let us see in once again. So here you have this train of weighted impulses, or you can say direct delta function. So this is your, if I take the samples, so this one is the signal at 0, then the impulse at t, or say I'm taking the sampling period as ts, so ts, and this one is at 2ts, then 3ts. Fine. Now here you can see the width. There is no width over here. This one is minus ts, minus 2ts this way. So this is called the train of impulse function. This is your train of impulse function, which is used as the sampling function in case of, which is used as the sampling function in case of impulse sampling. Or you can say with the message signal is multiplied with this signal in case of instantaneous or the ideal sampling. Now, how we are writing this mathematically? This is a delta function. So delta t minus n ts. If you see this, if you put the value of n equals to 0, then it is only delta t, which is this one, right? Now, if I put n equals to 1, this one is at t equals to 0. If I put n is equal to 1, it will become delta t minus ts. So it will have a value equals to 1 at t equals to ts, and other points it will be 0. So that is the thing you see over here, that at this point at ts, the value is, here it is continuous time, 1 is taken, so that's why. Otherwise, if you take the discrete time, then this one is 1 over here. Fine. Okay, this way we are going, if you write it completely, this full thing, if you represent mathematically, how will it be? Delta t minus nts, and there will be a summation from n equals to minus infinity to infinity. N is equal to minus infinity to infinity. This is the mathematical representation of the impulse signal. Okay, train of impulses. So keep in mind, this is train of impulse. If you take a single impulse, then it is only delta t minus ts, whatever the instant you are taking the impulse, that is your time. Okay, so we were discussing the ideal sampling or the instantaneous sampling. What is the problem with this is that the impulse signal is not having any width. So the switch that we are using over here, this switch has to be closed in the switch has to be closed in a very small time. That means it requires infinite bandwidth, which is practically not possible. Hence, this method is theoretically studied, not practically realizable. Now, in this case, when you're doing the reconstruction, first let us see, we have already discussed this method when we were doing the sampling process, but still, for if I take the xt, I'll just go in very briefly because we have done this in ideal sampling method was only used to make you understand the process of sampling. So this is your message signal. This one is your train of impulses. train of impulses you are taking at this point. 0, TS, 2 TS, 3 TS this way. And finally, you will get the sampled signal. So how will the sampled signal look like? This one will be the sampled signal. Okay. Now, if I represent this signal as xt, x of t, the Fourier transform for this signal will be x of omega. If this one is your delta t, I have to represent it by delta t. The samples are taken at interval of delta of ts, so it is this one. Finally this one is your sample signal. We can represent it as gt or st, whatever you want. So I have taken this as gt. How we get it? Actually, how do we get it? Gt is equal to xt into means you're multiplying this with delta t. Fine. And what was the trigonometric Fourier series representation of this one was, because when you take the Fourier transform of this, it is going to be the x e to the power j omega t. So like here, I am writing the Fourier series expansion for this delta tst. That will make it easier for you. Or you can, for the simplified purpose, we have done it in the previous lecture. So here I will be writing it in the simplest form itself. What we can do is gt is equal to xt n is equals to minus infinity to infinity delta t minus n ts. Now if you take the full thing inside the summation, it becomes n equals to minus infinity to infinity. After the sampling process, x of nts delta t minus nts. This is one way, and the other way of representing was taking the trigonometric Fourier series representation for this delta tst. This also we have done. This one was what? 1 by ts cos omega st plus cos 2 omega st plus cos 3 omega st, and this way it was going on, right? So you can see the previous lecture for this type of representation. Here we are doing it in the other method. Actually, not the other method. We are just writing the representation. So this one is the case of instantaneous sampling. This is your instantaneously sampled signal. This is a final representation. If you take the Fourier transform of this, you are going to get g of omega is equal to, this one will be written as x of f minus nfs, and then it is going to n equals to minus infinity to infinity, and this one is going to be fs. So that is just a constant that you are multiplying. So finally, we have the following things regarding the ideal sampling method, that we are using a train of direct delta functions for sampling it. The sampled signal is represented by this form in the Fourier domain and in the time domain. This is the time domain. This is the Fourier domain. You can also write it in the trigonometric Fourier series representation. That is also given in the previous lecture. Here also it is given. You can see this one. This way is the Fourier series if you take the impulse function in the Fourier domain, then if you can write it in this manner, cos omega st, the trigonometric Fourier series representation, and then you can write GTS 1 by TS xt plus this way. Now the reconstruction, when you are taking recovering the signal, ideally sampled signal, if you are recovering it, then what we do is, see, we don't want all these values, 2xt cos omega st, all these are higher frequency signal, 2 times of omega s. This is 1 time of omega s. This is 3 times of omega s. After this, there will be more higher frequencies. So we don't want all these. We only want xt. because xt is our message. So what we are going to do is we will pass this GT. We are going to pass this GT through a low pass filter. The low pass filter will reject all the higher frequency component and it will take only this xt. And also we don't want this one, then this ts, so we are multiplying with a gain that is equal to the reciprocal of the sampling period, and then through a low pass filter to remove the high frequency components of the signal. So what we do in case when we are recovering the ideally sampled signals, then we are passing it through the gain which is equal to the reciprocal of that sampling period, and then we are passing it through a low pass filter where its frequency, cutoff frequency is equal to the sampling frequency. Fine, and then you will get the original signal, that is xt. So from here you have passed gt and you have recovered xt. gt was your sampled signal and this one is your recovered signal or the original message signal. Fine. Okay, now let's move to the next one. That is your natural sampling. So in case of natural sampling, this is a practical method of sampling. Finite width of the sampling function. So the rectangular functions are used, rectangular pulses are used. Train of periodic rectangular signals are used as sampling function. Train of periodic pulses of width tau. So over here you can see the signal, the circuit also. There is a MOSFET which is used as a switch and a capacitor. So let's understand how is it going to work. So the switch MOSFET is working as a switch over here. Then whenever the gate voltage is applied at the MOSFET, then the capacitor starts charging. It charges for the duration the signal is on, means the switch is on. Let us see over here. In case of natural sampling, finite width periodic rectangular pulses are multiplied with the original message signal. This results in sampled signal at specific time sampling instance. And the top of the rectangular pulses, they are following the shape of the message signal. You can see over here, this is your message signal. This is the train of rectangular pulses. It is having a certain width. During this width, this switch is on. Fine. And the capacitor is getting charged. Fine. After that, when you are getting the sampled signal is following the message signal. The top of the sampled signal is following the message signal, the shape of the message signal. So how we are doing it mathematically? Taking the message signal or the input signal and the original signal and multiplying it with the sampling signal. Sampling signal here is the rectangular function. So we are taking xt and multiplying it with rect t, that is a periodic rect t. And then we are getting a sampled signal. How we are doing it in circuit wise? We are taking up the input as the message signal or the original signal. Then we are using a switch. The switch can be any device, MOSFET or transistor. MOSFET is a good switch. So we are taking the MOSFET and then we are putting a capacitor. The charging and discharging of the capacitor is decided by the switch over here. The duration for which the switch is on, the capacitor is getting charged and it is sampling. And after that, then it is taking the shape of the message signal. So this is the signal spectrum if you see it in the Fourier domain. So this is the spectrum of the message signal and this is the spectrum of the sampled signal. So let us see once mathematically what is happening for the case of natural sampling. So here we will see the case of natural sampling. So here what is the difference is that the sampled signal, that is GT was your sample signal. Okay, GT is equal to XT. Fine. Okay, first let us take some. Fine. So if I'm taking the sampling signal as ST, so ST is fixed for a certain duration. Say we are having the width as the top amplitude as A. So these are your rectangular pulses. of fixed duration tau. All of these are having a width tau. And you can see the sampling period is Ts. So the sampled signal, that is your GT, GT will be equal to XT when there is a when this the switch is on, or when this is from this duration till this duration. So what we can write, when CT is equal to A. Sorry, the sampling signal is represented by ST. So when ST is equals to A, and 0 when ST is equals to 0. Now let us represent this ST. ST is your sampling signal, or the rectangular signal over here. So ST is your rectangular pulse. The rectangular pulse is written in the period. So this one is the periodic rectangular pulse. If you take a single, it is something different. So what we are doing, we can write it in this form. That is n is equal to minus infinity to infinity. You are having so many signals over here, so many rectangular pulses over here. Tau A by Ts. I'll explain everything over here. Tau A by Ts sync. In the numericals on sampling, we discussed this part. Sync Fn tau e to the power j 2 pi f s n t. This is your ST. So how are we getting this? See, any periodic waveform. So from here, if there is certain amount of maths involved, we have to go through that just for, you can either remember this thing or you can understand the whole part. So let me tell you the full part. If you are taking any type of periodic waveform, it can be represented in trigonometric, in exponential Fourier series. Now, we will not be taking the trigonometric, because in that case, you will have to write for both sine and cosine. We'll be taking the exponential Fourier series. So it can be represented at this part, like this, e to the power j 2 pi nt by t naught. And this n is changing from minus infinity to infinity. So what is happening is, this is 2 pi by t naught is what? F, right? So f s nt e to the power j f s nt. That is your Fourier series in exponential form. Fine. Now this t naught over here is equal to the period of the sampling period, right? T naught is equal to Ts is equal to 1 by Fs. Again, F naught is equal to what? It is equal to Fs is equal to 1 by T naught. So this is the period of this ST. So this is the period of ST, and this is the frequency of ST. Period and frequency of ST. What is ST? ST is your sampling signal over here, the rectangular pulses, right? Now, when you are taking this is your Fourier coefficient. This Sn is your Fourier coefficient. If you write this Fourier coefficient, Sn, the expression for this, if you solve for it and get the expression for this, it is going to be Sn is equal to Ta by T naught. A is your amplitude, T naught is your period, and capital T is the width, pulse width. That is, we have taken as tau, right? So that, if you write in the Fourier domain, it is sync. I discussed in our previous class that The rectangular function, if you transform it into the frequency domain, it is a sinc. And the sinc function, if you transform it, then it is a rectangular pulse. So those are the duality. Sn is equal to Ta by T naught. Now from here, if you see, we can directly write it that S of T, we can directly write it that St without going into the details, because see, the thing is that we have to derive all the frequency transform over here, so that we are not going to do. I just showed you how what is what, and now we can do it in a separate lecture, how to get the Fourier transform of rectangular and sinc. I will give a certain different video on this, that you will, and in that you will understand. So this is tau A, because our width was tau A by Ts sinc Fn tau. And since it is periodic, that's why we are putting this e to the power j 2 pi fs nt. Now this has to be given the n is equals to minus infinity to infinity. Now finally, when you are writing the gt, that is your sampled signal, what is going to happen? You are going to multiply this with xt into st, right? So after this, the sampled signal in this case is going to be the tau A by Ts, n is equals to minus infinity to infinity. The same things I'm writing, right? Only xt will be multiplied. Sinc f and tau e to the power j 2 pi fs and t. This is pi into xt. That's it. That's your sampled signal in the case of natural sampling. If you want to take the Fourier transform of this gt and represent it in the Fourier domain, then this is going to be g of omega or g of f, whatever you call it. So the g of f, if you write it, this g of f is going to be the Fourier transform of g of t, tau A by Ts. Again, if you take the Fourier transform of this part, you have to take just the Fourier transform of this part. Means you have to take the full thing, but still, what are you going to get is the summation over here. N is equals to minus infinity to infinity. And then sinc f and tau x of f minus nfs. Fine. So here what happened, that if you take the Fourier transform of this e to the power, then that is going to be delta function, and delta function multiplied by xt will give you x, capital X in the Fourier domain. Fine. So this one was the naturally sampled signal. If you take the spectrum, if the Fourier domain representation is this one, then the top you can see it is following the message signal. Okay, now let's move on to the flat top sampling. This is again the practical method of sampling. Finite width of the sampling function, same, the rectangular samples are used. The same representation will be there, train of periodic pulses of width tau. Top of the sampled signal is kept flat. In case of flat top sampling, you can see when the message signal, when the instantaneous value is taken, that instantaneous value is retained. It is not following the message signal, the top of the message signal. The message signal is multiplied by the periodic train of rectangular pulses of finite width, means the sampled function in both the cases are same. This method, however, differs from the natural sampling method, as the top of the sampling function is kept flat. How is it done? This is achieved by holding a starting instantaneous value of the message signal for the entire finite width duration. This result why is it important? Because it is easier in reconstruction. However, it gives rise to the aperture effect. So we will understand what is the aperture effect. First, let us do this flat top sampling. This, that delta t minus nts was your impulse function with width 0. that has been transformed into HT with width, say tau, not 0, width was tau. Now this tau is multiplied, this HT is made a train of impulse by shifting it by certain duration. So that duration was what? For us, it was NTS. For every instant, we are separating it. Now this one, finally, the sample signal is my S tau into HT minus tau. S tau was what? S tau was a message signal multiplied with the impulse with some width. Just the impulse is given certain width. This is the process that has been taken for explaining the flat top. Because you cannot take the, you can take the rectangular function also, but this is another method that you can use for this one. See, actually, we are taking a rectangular function only, but we are representing it in a different manner. That's it. Now, flat top sampling, there is a problem which happens that is called the aperture effect. When sampling a signal with technique of flat top sampling, it introduces amplitude distortion in the signal. In this, high frequency signals are suppressed. This is also called high frequency roll-off, which attenuates the upper portion of the message signal spectrum. Larger the time period of the signal, more predominant is the aperture effect. To overcome this effect, we are using an equalizer in the reconstruction process. During the reconstruction, we will be using an equalizer. So what is happening over here is, let us see. This is the flat top sample spectrum. If this part is overlapping here, that, see, it's not shown here, right? Okay. Okay, let us see over here. When you are doing the using the flat top samples, then what we are doing is basically we are taking the, suppose I am explaining for this sample. Here I took take a sample. Now these portions, these extra portions are going to produce the aperture effect. These are going to create the aperture effect. Because these high frequency component over here, you can see high frequency roll off means these higher parts are cut. That is the high frequency roll off, which attenuates the upper portion of the message signal spectrum. So upper portion means the higher message signal, higher frequency signals are attenuated to a larger extent, which if you are taking the time period very large, in that case, more of the aperture effect is predominant. So to overcome this, we use an equalizer. Okay, now for both the natural and flat top sampling, the reconstruction process, what we use is a reconstruction filter and an equalizer in case of the flat top sampling. So, however, for compensating for the aperture effect in case of flat top samples, an equalizer is cascaded after the reconstruction filter. Interference of noise is minimum in case of natural sampling. However, flat top sampling is most popular among the three, as in the case of natural sampling, the removal of noise at the receiver is difficult. Whatever noise is coming, that the removal is becoming difficult in case of natural sampling. But the interference is minimum in case of noise because it is following the spectrum of the message signal, right? At the receiver is removal of noise at the receiver is difficult as the top of the signal follows the value of message signal, and noise is generally affecting the amplitude, not the time period, not affecting the time period in case of the noise effect. Fine. So this is all about the natural flat top and instantaneous sampling. Again, once if you go in a very short manner, here your sampling function is a Dirac impulses, train of impulse functions. Here in both the cases, the train of rectangular pulses are there. In this case, you are using the circuit. If you see, the switching sampler is used. In this circuit, what you are using is a MOSFET as a switch. In this circuit, for the flat top sampling, you can use the two switches. That is, one switch can be for this better diagram. I'll give this for this one. There can be a sample and a discharge switch. So I'll show this is not the appropriate diagram. Just 1 minute. Just take this diagram for the flat top sampling. What you can do is, you can take this one For this, you have to follow a different process, but this can also be used. So two switches can be taken simultaneously. One of the switch will act as a sampler and the other will act as a discharge switch. We will explain, we are using this type of switches in case of PAM signals. So in our next lecture, we will do this. This can be used for the flat top sampling. However, you can use this one also, but you have to keep the duration, means the amplitude, you have to hold it. Fine. That is the one problem that can happen. Rest, the difference is clear. I hope you have understood the differences between them, how we represent it mathematically. Again, for the mathematical purpose, you have to keep in mind that here we are multiplying with the Dirac function. Here we are multiplying with, in both the cases, we are multiplying with the rectangular functions. And while representing, what you are taking is, in this case, you will take directly, you will take the rectangular function. In this, you can take the impulse function, but with multiplied with a constant, you can say a unit step sequence. And that unit step sequence multiplied with the impulse will give certain width and keep the amplitude constant. That is it. Here in both the cases, you are using MOSFET as switch. You can take two MOSFETs in this case of flat top sampling. Here with the one MOSFET, it will go one MOSFET and one capacitor. Here two MOSFETs and one capacitor. So this is all. And in the reconstruction process, what we are taking is the reconstruction filter and an equalizer for the flat top samples and natural samples. And in the case of ideal sampling, what we take is the low pass filter and low pass filter and the multiplying it with the gain equal to the reciprocal of the time period. Okay, thank you everyone. So this is all today. Let's meet for the next lecture, that is the PAM.